Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to the Spot On Weather. This is the 2022-23 Winter Forecast Part 3. And in this particular part of the Winter Forecast series, I'm going to discuss climate drivers. These are also known as teleconnections, and they play a very, very important role in the overall winter weather across the United States, as well as the other mid-latitude locations such as Europe, Asia, anywhere in the Northern Hemisphere, really. And so I'm going to go ahead and delve into this. A little funny picture to start this video from the movie Elf. Will it be a winter where you're gathering a bunch of snowballs from the ground, an above normal snowfall winter, or will this be absent, these snowballs, for the course of winter? Of course, this is one of my favorite parts of the movie, when him and the little boy here, the younger boy, how they gather these up and win that snowball fight. All right, so let's go right into the discussion on climate drivers. We're going to start off with the Madden Julian oscillation, the MJO. I first want to talk about MJO and the circulation pattern involved, whether we have downward sinking motion or upward rising motion of air. And this is very important because what happens in the equatorial Pacific and Indian Ocean really can have impacts all around the world. And you can see on this map on the right the global impacts of the Madden-Julian oscillation, depending on what phase the MJO is in at a particular time during the winter season. Just here in the United States alone, the MJO can tie into the storm track across the Pacific Ocean, what the jet stream looks like. It can also tie into the potential for atmospheric rivers into California, which cause extensive flooding. Additionally, the MJO can tie directly in with some of the weather, more severe weather, thunderstorms, you name it. It can pretty much tie in with global impacts. And of course, there's more here than just over the United States. There's fires over Australia. There's a little bit of fires over Africa. And then we have monsoonal moisture during the monsoon season, heavy rains going into India. So the Madden-Julian oscillation has some global impacts, and that's exactly why I'm opening up this particular part 3 of the winter outlook with these type of climate drivers or teleconnections. Here is the overall circulation when we talk about the Madden-Julian oscillation. What it really is an eastward moving pulse across the equatorial Indian Ocean, eventually over into the western Pacific. Generally fades after a certain point in time as this enhanced area of precipitation and convection migrates toward the east. I'll show you the phases here in a moment and how that really impacts United States weather. But in general, with MJO, we usually have some rising air motion. This is an example of the phase where the rising air motion is over the Indian Ocean, and then we have some sinking vertical motion over the western Pacific in this particular case. But you really can see this complete cell that develops. Again, here's the motion. It's east across the equatorial areas there, the tropical areas from the Indian Ocean into Indonesia, to the maritime continent, on into West Pacific areas. These are the different phases of the Madden-Julian oscillation. Always paying attention to the Madden-Julian oscillation. In general, we have phases 1 through 8. Generally, when you have convection off the east coast of Africa, it's phase 1. That's where the enhanced precipitation, convection, the clouds are occurring. And then as it moves east, it moves into phases 2 and 3 typically. And then the maritime continent, Australia, phases 4 and 5 is where the enhanced convection is located during those phases. And then phases 6, 7, and 8. As we get towards 8, we get closest to the international date line at that 180-degree west longitude line. Very important to pay attention to what phase. Where is the enhanced convection occurring? Where is that enhanced cloudiness and precipitation occurring? The convection across the tropical areas. As that does set off a larger scale circulation pattern that expands well beyond the Indian Ocean and the West Pacific, and again has impacts on the world's weather. Looking at the latest forecast, I want to explain the diagram here, and I usually do this on my teleconnections discussion, my weekly videos during the fall and winter season. This is an example of a phase diagram, And the inner circle, whenever the line is within the inner smallest circle, that indicates that the MJO is basically in a null phase, or a non-consequential phase for the weather across the globe. The further away these particular lines get from the inner circle, that smaller circle here at the center, the further away these lines get from the center, the greater the magnitude or amplitude of the MJO phase, and the greater the impact on global weather. In general, what we're showing here is the latest forecast. It's a 30-day CFS. This is the CFS, Climate Forecast System forecast. And so you can see the dates attached to it, like next to every dot here every so often on these lines. These lines represent various members showing various possibilities of amplitude for the MJO forecast. This one runs out to the end of October, the end of this month, 2022. But in general, you see a general motion starting out here just right on the inner circle border there to phase 2. And you see how the amplitude generally increases as we go through the month of October, as the MJO is forecast to move into phase 4, phase 5, phase 6, and ultimately into phase 7. You'll notice the different regions are generally labeled here on the phase diagram. The Western Pacific, you have convection, generally phases 6 and 7 here. That indicates Western Pacific enhanced convection. When it goes to phases 8 and 1, that's where we go into Africa. You can see 8 and 1 involves Africa, whether it be the west coast or the east coast of Africa. And then phases 2 and 3 is generally where the enhanced convection and precipitation is occurring over the Indian Ocean. And then phases 4 and 5 is the maritime continent. And the maritime continent refers to areas of Australia there, okay, Indonesia and Australia. So this is just an example of what we pay attention to closely during the fall season, during the winter season. The MJO can play a significant role in the weather across the United States. Certain MJO phases, for example, favor the development of an upper-level ridge off the U.S. southeast coast, which results in very mild weather across the east, whereas phases 8 and 1, and even 2, tend to result in much colder temperatures and more of a trough configuration. The jet stream takes more of a dip in the eastern United States in phases 8, 1, and 2. Now, these temperature composites, I'm showing you an example here on the right. These temperature composites change throughout the course of a year. I'm showing you the meteorological winter months of December, January, and February for the temperature composites for the various phases of the Madden-Julian oscillation, or MJO. Notice the blue shading on these graphics generally indicates below normal temperatures, and then the orange coloring indicates above normal temperatures. All right, so generally phases 8 through 2 are below normal, fairly cold across the eastern United States for the months of December, January, and February. So if this particular MJO is in phase 8, 1, or 2 and is fairly amplified, we can see some below normal temperatures across the east. Whereas phases 4, 5, 6, they tend to be the warmest phases of the MJO, support the development of upper-level ridge with a long wave pattern off the east coast. Phase 7 is also very mild, but not quite as drastic as, say, phases 5 and 6. You can tell by the shading of the orange coloring here. The darker the orange shading, the greater the above normal temperature anomalies. So in general, MJO is a very important climate driver or teleconnection that we need to take a close look at. Some seasons in the winter, this is pretty much non-existent, and it remains in the null phase. Overall, it just kind of rotates around the convection, generally between the different areas, the Africa, Indian Ocean, Maritime Continent, and West Pacific, but it tends to remain minimal in its impact. The amplitude is not as great, so it stays within this inner circle. Other winters, this can really make a significant impact and can overpower the other teleconnections or climate drivers. Let's take a look at last winter's MJO. And what I did is I just took a shot. This is courtesy of the NOAA Climate Prediction Center. I just took a shot of, this would be mid-December on the far left. This is mid-January in the middle. And then this is mid-February on the far right. So if you take a look at the green line here, that's a line I want you to pay attention to. In general, for mid-December, right on through early January, the MJO is forecast to be a little bit stronger amplitude into phase 7, and then eventually working its way into phase 8. So what do you think that meant for our temperatures? Let's take a look. We looked at the months of December, January, and February, and we look at phase 7 and then phase 8, right? Phase 7 is still somewhat above normal, but then as we transition to phase 8, it gets colder than normal. That's exactly what happened last January. It took a little bit of time because December was a very, very mild month in the East overall. But eventually, as this MJO worked towards phase 8, it was fairly good amplitude there, away from this small inner circle. It did cool off. It did get much colder. Here's January 17th through January 31st of 2022. Notice what happens, though. Over time, where the green line is, it's staying within this smaller inner circle. So the MJO rotates into this null phase from January 17th to the 31st of 2022. So at this point, we'd expect other teleconnections or climate drivers to kind of take over at this point. MJO would be more negligible or minimal impact. Looking at the far right here, what happened as we moved into late February and early March, the MJO rotated around into phases 3, 4, 5, and 6. So what does that mean for February? MJO phase 3 through 6, right? So phase 3 starts to get a little milder. Phase 4 getting even warmer than normal. Phase 5 and phase 6 very warm across the eastern United States. So that's exactly what I would be forecasting based on the MJO diagrams or these plots. Okay. And again, one more thing to make note of: the temperature composites and the phases of the MJO. This changes throughout the course of the year. So if I were to look at March, April, May's temperature composites, they'd be different than, let's say, December, January, February. So, for example, phase 2 might be indicating colder than normal temperatures in December, January, February, but it may be that same phase 2 may be indicating above normal temperatures in a different time of the year. So now let's take a look at something that I think may have an impact on this year's winter weather across the U.S. And again, we talk about enhanced convection, rising air motion. Where is it occurring in the tropical areas? In this case, we're going to look at the Indian Ocean. This is known as Indian Ocean Dipole, IOD. What happens here, we have two boxes, and they do have specific latitude and longitude coordinates. I don't have them on me right now, but this is just kind of showing you where the east box is. This is considered East Indian Ocean. This is where we analyze the sea surface temperature anomalies. And this would be the western box, the West Indian Ocean box, where the sea surface temperature anomalies are monitored. Now what happens when you get a warmer than normal water temperatures there in the Eastern Indian Ocean and cooler than normal waters there in the Western Indian Ocean? We call that a negative IOD, or Indian Ocean Dipole. This is the sea surface temperature anomalies from late August of this year, 2022, showing a negative IOD. Okay? So what happens, again, negative IODs has warmer water in the Eastern Indian Ocean and cooler water in the Western Indian Ocean. Now look how the IOD changes over time. And you'll notice, I read an article recently that said due to global warming that the probability of more positive IODs is increasing. So with a warming planet, we're looking to have more of these positive IODs. So anywhere above the 0 line on this graph indicates a positive IOD. You'll see it here in the reddish shading here, the red outline, the pinkish shading or salmon color. Look how strong the IOD was on the positive side when it came to the 2019 into the 2020 year. This was really, really above normal. In fact, these temperatures were generally we're looking at almost 2 degrees Celsius above normal temperatures for the IOD, these anomalies on the positive side. So positive side, by the way, excuse me, positive side is the flip-flop of this. So a positive side would have the warmest ocean temperatures across the Western Indian Ocean and the coolest temperatures in the Eastern Indian Ocean. So I just wanted to clarify that. There were some winters or some years where the IOD was also negative, and this was a sharply negative IOD back in 2016. Now, what about the circulation with IOD? All right, so with a negative phase IOD, this is what happens. You get rising air motion over the maritime continent in Indonesia And that enhanced rising air motion results in a lot of showers and thunderstorms, increased convection, and there's your warmer than normal water temperatures of the negative phase IOD. So above the warmer than normal, above the warmer than normal sea surface temperatures, you generally have rising air motion. Over the cooler than normal water, you tend to have sinking air motion across the Western Indian Ocean. So this is the negative phase of the IOD. Okay, so what happens when we have a negative IOD? This is the temperature anomalies that we see across the United States during negative IODs. We're currently in one right now. The white coloring here indicates near normal temperatures, the blue below normal, and then that salmon and the pinkish colors, the reds, they indicate above normal temperature. So with a negative IOD from December to February, you see there are a lot of above normal areas across the United States. The Midwest, the northern plains, right on down into the south central U.S., the Ohio Valley. Below normal temperatures actually are across Texas and Florida. And then near normal temperatures for the mid-Atlantic and New England. As far as probability of precipitation during a negative IOD in the wintertime across the U.S., green coloring or blue or green coloring indicates above normal precip. Brown coloring indicates below normal precip. So not only are we warmer than normal across the northern plains, but we're also drier than normal. And then across the eastern U.S., we're wetter than normal across the mid-Atlantic specifically and across parts of Texas and New Mexico. All right, so that's the IOD. That is the IOD, and let me take a minute here. Okay. I have a tickle in my throat as I'm talking. It's a lot of allergy action here, so please bear with me. I apologize for these occasional interruptions, but just trying to push through the video here. And I'll keep moistening my throat to keep it at bay. All right, so now let's talk about what's known as the Pacific Decadal Oscillation, the PDO. With the PDO, generally we have two phases. We have a positive phase here on the left and a negative phase on the right. This is showing you the sea surface temperature anomalies in the Eastern Pacific, generally the Pacific overall. So you'll notice we pay close attention to when there's El Nino and warmer than normal water temps in the equatorial Eastern and Central Pacific, or when it's La Nina like we have now, where we have below normal water temperatures in the Eastern and Central equatorial Pacific. But we also have to pay attention to the mid-latitude sea surface temperature anomalies up in the Pacific, specifically the Eastern Pacific. Now, when we see warmer than normal water or above normal water temps in the Eastern Pacific, this generally is called a positive phased PDO, or Pacific Decadal Oscillation. When we have cooler than normal water along the Eastern Pacific, that generally indicates a negative phase of the PDO. All right, so here's an example. Why does the PDO matter? Here in the bottom left, we've shown correlation between December and through February temperatures in the U.S. and then December to February PDO index. So with a positive PDO, you generally get colder than normal temperatures from the deep south, southeast, up to the mid-Atlantic, and even all the way up into New England. So generally the east is cooler than normal during a positive PDO when you have warmer than normal temperatures off the Eastern Pacific. And it's also warmer than normal across the western U.S. in a positive phase PDO. Look at Alaska. Alaska's super warm when it comes to a positive PDO phase. Look how the PDO varies over time. This is showing you blue would be the negative phases and red would be the positive phases. Generally showing you the temperature anomalies in degrees Celsius. So you can see a lot of blue bars here going below the zero line. That is indicative of a negative PDO phase with cooler than normal water over the Eastern Pacific. And then the red would indicate a positive phase PDO where you'd have warmer than normal temps in the Eastern Pacific. So it's cyclical, but we can kind of see that the negative PDO has kind of been like the boss lately. Well, at least going back to 2000, the year 2000. There's a lot of years that show a negative PDO. All right, so here's some big notes here at the bottom. Note that when the PDO is positive, we generally have these colder temperatures across the eastern United States. And one other important note is with a positive PDO, it generally yields a positive Pacific North American pattern, a PNA pattern, where that favors the upper level ridge and warmest temps in the western U.S. and a downstream trough in the eastern U.S. So this really does tie in together. The PDO phase and the PNA pattern, Pacific North American pattern, they tie in together. That impacts the orientation of that long wave, the jet stream overall, the axis of the jet stream. Right, speaking of PNA, let's talk about the Pacific North American pattern. All right, so for a positive PNA, what happens? We generally have an upper level ridge positioned over the western U.S. and western Canada, and a downstream trough into the eastern U.S. So an upper level ridge in the west, a downstream trough over the east. And generally that means it's more unsettled and colder than normal in the east and warmer and drier than normal in the west when we have a positive PNA, Pacific North American pattern. When we have a negative PNA, we generally have the trough over the western U.S. and western Canada with cooler and wetter weather. And then we have a ridge over the eastern United States with a negative PNA. It's warm and dry over the southeast up to the mid-Atlantic. Generally, the east is really warm. Here's some real-time differences between a positive and a negative PNA pattern. Note, with a positive PNA phase, you generally get this troughing further back into the Gulf of Alaska and right in the vicinity of the Aleutian Islands. And then downstream of that trough, you get an upper level ridge parked over the western U.S. into western Canada. Sometimes these ridges can go all the way up to the polar areas. They can be that amplified. Downstream of that ridge, during a positive PNA, you get troughing and cooler and wetter conditions across the eastern U.S. This occurred in February of 2016. That's this map here. Now, what happened in February 2019 on the right? We got an upper level ridge into the Gulf of Alaska. This is a negative phase of the PNA. That upper level ridge was basically over the same location that this trough was in the Aleutian Islands during the positive phase of the PNA. But now in the negative phase, we have the upper level ridge of the Eastern Pacific and the Gulf of Alaska. We have a downstream trough into the western U.S., cooler and wetter conditions across the western U.S., and then another ridge setting up over the eastern U.S., resulting in warm and dry conditions during a negative phase. So it's very important to take a look at the PNA pattern as well. Here is the last winter's PNA. In general, we only have three. By the way, we had a strongly negative PNA. Let me start with last winter first. We did have a strongly negative PNA in December of 2021. And as a result, what happened in 2021 in December? Look how strongly negative it was. See how much more amplified that is in a negative phase? That resulted in very, very cold temperatures into parts of western Canada, extremely frigid, on into the Pacific Northwest in December. And then with time, what happened is the PNA climbed back to the positive phase above the zero line here for pretty much January all the way through most of the rest of the winter, actually. But in January specifically, you can see the amplitude, how higher this PNA got as compared to December when it was in the negative phase. So this PNA can change on a short order is what I'm getting at. And by the way, there's only been 3 La Nina winters since 1950 that have had a negative PNA all 3 months of the winter. And there's only 1 La Nina winter which had a positive PNA in all 3 months of winter, and that was the 2011-2012 winter. The positive PNA lasted all 3 months, December, January, and February. Here's an example of a positive PNA This just generally showing you what it looked like back in 1981 in January. We had a very highly amplified ridge across western U.S. and western Canada, all the way up to the polar areas. And the higher this ridge builds, the greater the probability that much colder air is going to dump out of the Arctic areas into the eastern U.S. So we had below average heights in the eastern U.S. in January of 1981, and we had much above normal heights in western U.S. and Canada. So this is the typical trademark of a positive PNA. Now let's move on to the Eastern Pacific Oscillation, the EPO. Now, the EPO overall, the big differences here is positive graphics here on the left and negative EPO pattern graphics on the right. And so with a positive EPO pattern, what you get is a faster west to east zonal oriented jet stream that tends to flood the whole U.S., the lower 48, with milder Pacific air from coast to coast when the EPO is positive. Here's an example of the temperature diagram. Now, one other thing about a positive EPO pattern, it produces a very cold pattern across Alaska. Very cold. And generally milder as mild Pacific air dominates the whole United States. Look at how warm it is across the whole U.S. during a positive EPO. Now, a negative EPO pattern, look what happens here. We get a huge ridge that builds into Alaska. That's that big ridge, and then you have a trough over the eastern United States, or eastern North America in general. So with a negative EPO, it tends to produce the flip-flop pattern of a warmer than normal situation in Alaska and a colder than normal situation for the United States as a whole during a negative EPO. So, there's always an equal and opposite reaction to everything in the atmosphere, and this is another example of that. Right now, let's talk about some of the major climate drivers we need to talk about for the upcoming winter. The first one is the Arctic Oscillation AO. I'm just showing you a difference between positive phase on the left and a negative phase, the AO on the right. So notice the jet stream again. During a positive AO, low pressure remains in the higher latitudes over the poles, and then you get higher pressure in the mid latitudes, okay? So you get more of a west to east oriented jet stream, zonal jet stream. During a positive phase, the AO, coldest air remains up further north. With a negative phase AO, you get this huge amplification in the polar front jet stream. In the negative phase AO, you get a strong ridge up into Alaska. You get a deep trough in the eastern United States. And you generally have high pressure now with a negative AO up at the poles and lower pressure over the mid-latitudes. And by the way, the AO is a predictor of the polar vortex. I will get into the polar vortex in part 4 of the winter forecast series this year. But just keep in mind that the behavior of the polar vortex dictates really how the AO will behave. So when you have a positive AO, it generally indicates a stronger polar vortex, and then a negative AO equals a weaker polar vortex. Here are some examples of positive and negative AO years. You can see the late 80s into the early 90s were dominated by a very strongly positive AO. Even the mid-90s, 94, 96, or 94 to 95, strongly positive. And then look at some of these amplitudes. The winter of 2020 had a strongly positive AO. The blue coloring here, blue spikes indicate much below normal. One of the more infamous events of a negative AO occurred during the 2009, 2010. There was some it's just record amplitude negative AO in that particular time frame. Look at last season's AO. In general, if we look at the AO, any of these blue bars in the vertical, if they're above zero line, that means positive AO. If the vertical blue lines, blue bars are below the zero, that's a negative phase of the AO. And so this runs generally from 4 November right through 3 March of 2022, by the way. And so if we just pay attention to the top here, you'll notice in December how strongly positive the AO was, which would indicate more of a faster moving west to east jet stream, milder conditions across the U.S. as a whole. And that positive AO tied in with a stronger vortex, polar vortex, and also tied in with that negative PNA, and resulted in very mild temperatures across the eastern United States. So Look what happened here from mid-December and early January, however, of last winter. The AO went negative, and at that point, that's when, especially a couple weeks after this point, the surface temperatures really did get much colder across the eastern United States. So basically, negative AO is going to favor colder than normal temperatures across the eastern U.S., and a positive AO will generally indicates above normal temperatures across the eastern U.S. during a wintertime. 2021-22 winter season can be summed up by a positive AO in early December, transition to a negative AO in late December and early January. Then after that, mid-January on, it was pretty much positive, the Arctic Oscillation the rest of the winter. Right now, let's talk about the Atlantic Multi-decadal Oscillation, AMO. This one is very, very important as far as the eastern United States temperatures for the winter season. First, let me start here on the left. The orange shading indicates above normal sea surface temperatures. The green shading indicates below normal sea surface temperatures. And whenever you have the AMO, this is a tripole of water temperature anomalies. Okay, so you have three circles here. This is your tripoles here. We're comparing the water temperature anomalies south of Greenland in the North Atlantic. We're comparing the water temperature anomalies there off the northeast New England area of the U.S. over the North Atlantic. And then we're comparing the water temperatures in the main development region of the tropics. This right here is an example of a positive phase of the AMO, where we have above normal sea surface temperature anomalies south of Greenland, and we have cooler than normal temperatures off of the New England coast, the North Atlantic, and then again warmer than normal temperatures across that main development region in the tropics, the deep tropics and the Atlantic side. What's going on right now? So let's see. We have warmer than normal temperatures south of Greenland across the North Atlantic. Okay. We have slightly cooler than normal waters there off of New England. A lot of that had to do with the major upwelling event, which with storms generally tend to stir up the water, and sometimes they're strong enough to where they can bring up much cooler waters from the subsurface. This happened actually with a major hurricane that recently just went up towards Nova Scotia. And then also, we have slightly warmer than normal temps in the main development region of the tropics. So right now, this is based on today, the 2nd of October 2022 sea surface temperature anomalies. By the way, you'll notice that La Nina is showing up quite well across the eastern and central equatorial areas by the dark blue coloring below normal temps there. But generally, this is favoring a positive phase of the AMO right now. I'm especially concerned with this area south of Greenland. So when you get a positive AMO, what does that mean? That means you have warmer waters in the North Atlantic, south of Greenland. And guess what? A positive AMO generally leads to a tendency for a more negative North Atlantic oscillation, NAO, in the winter season. And I'm going to get to the NAO here in a moment. Very important oscillation we need to talk about. A negative AMO, on the other hand, a negative AMO would feature colder than normal water here, warmer than normal water here, and cooler than normal water here. So just kind of be the reverse of what I showed you for a positive phase AMO. A negative AMO would be cooler waters in the North Atlantic, south of Greenland, which would lead to a positive NAO. I will give you a little hint before we get to the NAO topic here in a minute. A negative North Atlantic oscillation, or NAO, negative NAO, leads to colder than normal temps across the eastern U.S. A positive NAO typically leads to warmer than normal temperatures across the eastern U.S. in the winter season. So, bottom line here is the AMO can ultimately drive the NAO phase. I am focused on what happens to this water south of Greenland, specifically over the next 3 to 4 weeks. You can see how much warmer than normal it is. Could have a huge bearing on our upcoming winter weather. Now, let's talk about that NAO, North Atlantic Oscillation. This is a big one. This is like one of the major oscillations that control the temperatures across the eastern United States during the winter season, and even into parts of Europe. Positive mode of the NAO, we have more of a west to east jet stream. The milder air is across the mid-latitudes into eastern North America, into parts of Europe. Southern Europe is actually cooler and drier during a positive NAO phase. You get a stronger high here in the eastern Atlantic. You get a stronger low there in the vicinity of Iceland. So you create a stronger pressure difference, a tighter pressure gradient. You're going to get a more west to east oriented jet stream. It's going to be moving fairly quickly. It's going to be moving. It's going to have acceleration in a west to east manner. Notice in a positive phase NAO how there's cold up in the northern latitudes and tends to be more sea ice. With a negative NAO, we have an opposite effect. So now we get that huge upper level ridge across the North Atlantic into Greenland. This is known as a blocking ridge or a blocking high. The high down over the eastern Atlantic, closer to the tropical areas, tends to weaken, and you tend to get a deep trough, upper trough across the eastern U.S., and it tends to be colder and more stormy across the eastern U.S. And if you get a strongly negative NAO, especially during the heart of winter, like in the January and early February timeframe, that is when we can see above normal snowfall across the mid-Atlantic up to New England with a negative NAO. Okay, so look at the differences in the jet stream. We have more meridional, a weaker jet stream, more meridional, more wavy, with a negative NAO as compared to a positive NAO. Look at the history of the NAO over time. We had a strongly negative NAO there in 2019. Last winter, we also kind of had a little bit of a negative NAO. I'll show you some examples here in a moment. But you know what's crazy about 2010, that time frame? We not only had a strongly negative AO, but we also had a strongly negative NAO at the same time. So this just set some crazy, crazy cold temperatures in very stormy situation along the eastern U.S. and just a lot of cold. So just in general, AO and NAO behavior is typically directly proportional to each other. So what the AO does, the NAO usually does too. So for example, if the NAO goes negative, then the AO usually is negative. Or if that NAO is positive, the AO is also positive. So they kind of work in sync with each other. Here's the previous winter season NAO. Isn't this just crazy? I would say, though, outside of mid to late December of 2021, last December, the NAO overall was predominantly positive last winter. See the blue bars here? Blue bars are above the zero line on the positive value side of things from 1 January right on in through 1 March. Not super strongly positive, but it was strong. It was positive nonetheless. The only negative time that we had really of last winter in December was late December. That was it. So bottom line here is the NAO, the North Atlantic Oscillation, describes the strength of the polar vortex. With a stronger polar vortex, you usually get a positive NAO, and that results in a stronger west to east Atlantic jet stream. Whereas a weaker polar vortex results in a negative North Atlantic Oscillation, NAO, and that's going to result in more of a wavy jet stream. The jet stream is going to slow, it just become weaker overall. North Atlantic blocking is going to occur with a negative NAO, typically up into Greenland. And then with that deep trough over the eastern U.S., you're going to get a lot of Arctic air, direct shots of Arctic air from the far north. Here is the correlation between eastern U.S. temps and the NAO phase, and they go hand in hand. Now, the U.S. temps are in the red line coloring, and the NAO is in the blue line coloring. But notice, whenever the NAO goes positive, you see the U.S. temps warm. Whenever the NAO goes negative, you see the U.S. temps drop. So it's almost like a mirroring image of each other. Now, are these two lines, these colored lines here, the NAO and U.S. temps, are they perfectly on top of each other? No. In fact, you kind of see some lagging effect here back in the early 90s in the wintertime when you saw a positive NAO, but you didn't see the warming of the temps until a little bit later. But look at this drop off from 2010 again. This is just, it blows my mind. Like that was one heck of a winter if you like cold and snow in the eastern U.S. if you live in the East U.S. But look at the drop off, how strongly negative the NAO was in that particular winter. Look at the temperatures, how they dropped too. Not quite as sharp, but they still did drop. Look at this, 1978 to late 70s. Look how steep these temperatures dropped in basically in correlation with the NAO going negative. So NAO, bottom line, is typically the best predictor for U.S. temperatures in the winter. So every year when I do the winter forecast, this is one of the biggest things I look at. All right, that wraps things up tonight on, we talked about here in part 3 of the 2022-23 winter forecast, climate drivers or teleconnections. We talked about the Madden Julian oscillation circulation. We talked about the importance of it. Where is the enhanced tropical convection occurring? Is it in the Indian Ocean? Is it over the maritime continent? Is it in the Western Pacific? Is it off the coast of Africa? Very important, because where that happens, there is this circulation cell that develops where you have upward rising motion and sinking air motion. So this does tie into our weather quite significantly, especially in the higher amplitude phases. Here were the phase diagrams I mentioned earlier. Here was last winter, December, January, and February, MJO diagrams, phase diagrams. And then we talked about the Indian Ocean dipole, what's going on over here in the Eastern Indian Ocean versus the Western Indian Ocean as far as temperature anomalies. During a negative IOD, we have the warmest above normal water temps in the Eastern Indian Ocean and the coolest temps in the Western Indian Ocean. And for the positive IOD, just flip that. In the case of a positive IOD, we have the warmest sea surface temperature anomalies in the Western Indian Ocean and the coolest in the Eastern Indian Ocean. That impacts the overall circulation there. Anytime you have above normal water there in that vicinity of the Indian Ocean, the equatorial areas, warmer than normal water is going to result in rising air motion, enhanced convection, whereas cooler than normal water generally tends to promote sinking air motion. But look at this particular circulation cell that develops just over the Indian Ocean alone. And here were the correlations of the negative phased IOD as an example. These were temperature anomalies, and this was precipitation anomalies. Looking at the PDO, Pacific Decadal Oscillation, we're looking at the differences between positive phase and negative phase. I have much more to say about these particular teleconnections or climate drivers in my final part of the winter outlook when I show you my predicted weather maps. In general, we're showing you an example of a positive PDO. A positive PDO occurs when you have warmer than normal water temperatures off the U.S. West Coast over the Eastern Pacific. Look at this cooler than normal water, by the way, during positive phase over the North Pacific. So it's really interesting to watch how these change. The PNA pattern, Pacific North American pattern, whether it's a positive or negative PNA matters. In fact, right now we're currently situated in a positive PNA phase recently here in late September, and it's forecast to continue in October, where we have a upper level ridge over the western U.S. into Alaska and a trough over the eastern U.S. And that is going to result in some below normal temperatures across the east with that type of configuration of positive PNA. Previous winter seasons PNA, we took a look at it. Last winter having that negative PNA in December, but then things rebounded into January where we had a positive PNA. And then EPO, just taking a look at the differences, whether we have a positive or negative Eastern Pacific oscillation, how the jet stream sets up, the orientation of the jet stream, that's going to dictate where the warmest and coldest temperatures are. Additionally, it's going to dictate where that storm track ultimately lies, who gets wetter than normal and who remains drier than normal. And then the Arctic oscillation, the AO, showing you the difference between the positive phase here on the left and a negative phase AO on the right. The amplitude, orientation of the pressure systems, as well as the positioning of the jet stream really do make a difference between positive and negative phase AOs. And then the AO is a predictor of that polar vortex. Remember, strong polar vortex, positive AO, weaker vortex, negative AO. There's last winter's AO, primarily a positive, believe it or not, negative in mid to late December. And then the AMO, Atlantic Multi-decadal Oscillation. Got to pay attention to these waters, and this is what I'm watching closely south of Greenland. Do these waters remain this much above normal as we head into the winter season? Look at the warmer than normal waters, by the way, in the Northwest Pacific. I neglected to mention that. But in general, we have warmer than normal waters there along the Eastern Pacific, right? So we talked about the PDO. So with warmer than normal waters along the West Coast, that's a positive phase PDO. What happens to the positive phase PDO when you have warmer than normal water over the Eastern Pacific, they're off the West Coast? This is usually the result, below normal temps in the East. So a lot of this stuff, you have to look at it all. You have to digest it. When I'm coming up with these winter forecasts, got to look at everything to really try to determine what could be the outcome this winter across the United States. And then there's your NAO. Again, AO and NAO tend to be like in alignment with each other. So what the AO does, the NAO does, and again, this describes the strength of the polar vortex as well. With a positive NAO, you generally have a stronger polar vortex over the polar areas. In the next video, I'm going to get into more on the polar vortex. Believe me, I'm going to dive deeper into that. And then the weaker vortex, you have a negative NAO, just kind of showing you the correlations of last winter, mid to late December last winter. The NAO was predominantly positive. And then the correlation between Eastern U.S. temps and the NAO. NAO drops and goes negative, so do the temperatures in the Eastern U.S. for the winter season. On the other hand, if we have a strongly positive NAO winter, the temperatures tend to be above normal, quite a mild winter. A lot to digest. I'm so excited. Thanks for sticking with me. Apologize again for those moments of where, have you ever got that tickle in your throat you just can't get rid of? That was me here at the beginning of the video. So I just got to keep working through it. Thank you so much for subscribing to the channel. I'm noticing the numbers coming up the last few days. Really enjoy sharing the weather knowledge with you guys. And, looking forward to the next video. We'll get into the polar vortex. We're going to get into the polar vortex next. Can't wait. Talk about it. Talk about its behavior, what it means. That is all I got for now, everybody. Until next time, take care and God bless everyone.